This is the NANOG panel on smart routing. We have lots of fun. The topics will be, what is smart routing? Smart routing or route control. Why did the enterprise customers want it? And what BGP issues has smart routing uncovered? The BGP issues will happen later on, after a break. Now I come to the fun part of the presentation. I've had a really great time over the last, I think 12 weeks, because I believe in starting early and finding out a whole lot with the panel. And so I told them they could sit in random order because it was a test to make sure I had the faces and the names. Several of these guys I didn't see until we actually got here. So I'm going to start over with Jeremy. Jeremy's the only one with a hat on, so he's hiding a bad hair day. The co-founder, Jeremy is the co-founder and director of NetVNG. He's also worked at Home and AT&T SurfNet, so I'm sure he's been around the block with networking. Jeremy's also been one of those people who just keeps sending in the slides and helping me figure out the next steps. I appreciate that. Next one is Aaron Britt. Aaron is here with the short hair, although Robert on the end is also got short hair. So the next thing is Aaron says he's just a network engineer, but we've had long discussions, so I assure you'll find lots more fun from Aaron. Proficient, we have Robert Bays. Robert's way on the end. Okay. Robert was with Digital Island, and he has the fun of being downtown San Francisco, which I think is pretty cool as far as an office. The last, Mike Lloyd is here. Mike is CTO of Route Science. He's employee number 5 only because the founders and another guy, the 3 founders and one other guy beat him to the restaurant when they were forming it. He was also with the Cisco VPN project and wrote the BGP simulator for Nexus. The last one I have is Brandon Ross, and Brandon and Dan Golding actually helped me a lot out of Sockeye, and he's the VP of Engineering at Sockeye. He also was Director of Engineering at Mindspring. So these guys have had a lot of experience and a lot of interesting things to say. Now, each of us in this panel have only so much time because they have a lot of interesting pieces. So at a certain point, Mike is going to stand up and you should all cheer because that'll mean it's my turn to be done. So let me just sort of go through some basic. As the moderator, what I did is you'll find a questionnaire on the web page. And in that questionnaire is what we actually asked each of these vendors to pull out because we were looking for exactly what happened. So first of all, let me just go through some introduction. First, there's the enterprise myth and reality. Remember, smart routing is trying to help the enterprise, the network from the enterprise's view. Many times we look at things from the ISP-centric view. Now take your eyes out, readjust them, and here we come from the enterprise. The myth that happens sometimes is that the internet is designed to be highly reliable and efficient even in the event of a nuclear attack. I think that came from Vince Cerf or something. The reality is, this is no surprise to all of us, that routing problems occur, failures are noticed by customers, and bandwidth is wasted due to over-provisioning. We'd also like to tighten that belt. Most enterprise routing, good thing for me to learn, didn't really use BGP policy. All that work we put into BGP policy is often not done. Some people say it's a Cisco marketing machine. Some people say it's lots of other things. I don't know exactly why all of them don't. Those who do use it heavily. So mostly BGP is left to the tiebreakers, and you see the BGP hierarchy of needs. There's the AS path length, the lowest origin, the MED. And as you see, there's very small variance in some of the AS paths. I think if you remember the CADA, and Casey promised she'd be hanging someplace around here for you to ask a question. The statistics at the last NANOG showed you how the AS path, and I would reference those to actually look at some of the statistics she sees. Then you go with origin, and very few percentage have BGP origin changes, and then you have MEDs. Now, the interesting thing is later in the statistics, you're going to find out that the information we have from each of these vendors and their appropriate customers varies. So this is real interesting. I mean, it's really interesting. We've never really seen a lot of studies from the enterprise viewpoint. Okay, but routing in the ISPs impacts the ISP, And performance is in the eye of the user. It's a function of the metrics, latency, loss, jitter, and what you feel is good. The shortest path doesn't also mean the best performance. So let me go through some introductions. What is smart routing? Basically 4 things. Number 1, you go out and you measure and probe the network. You have routes and traffic that flow through different important points, and you may use active UDP TCP flows, which I've classed into 2 classes, ping-like and traceroute-like. You may use traffic flows, which is snoop, sniff, served, and if you think of another way to find traffic, I'm sure these guys will add it. Traffic level measurement with NetFlow or SNMP, and BGP route data. So that's what you look, and then you store the information, and what you usually record is what you get. You select the optimum routes, insert the better routes in BGP, and report the information to the user. Seems fairly easy to understand what these guys are doing in the big. But, as a quote from my NANOG Plus person, Bill Woodcock, there's a lot of questions underneath that simple statement, like what to measure, is it loss, is it latency, is it packet length? It's not entirely obvious where, why, when, and how you should do this. Do you measure from the desktop machine who buys the software, or do you measure from somewhere or some large set of somewheres that might be representative? The real art is in how you measure and what you do. Do you measure some sort of generically frequently viewed websites? Or, although this is likely to annoy these proprietors of the websites if the tool becomes popular. Or what about some routers within the backbone? Although someone might get wise and say, you ping me again, you die. Excuse me, that's not Bill, that's me. Or some set of routers within the backbone architecture, although someone may get wise and put them on private addresses or cause them to stop wasting cycles in response to your tool. Is there even a right answer? It may be that one size doesn't fit all. That's from the NANOG pages just a couple days ago, which is interesting. So there is a continuum in how this era is working. You see what is monitored. They look for user paths, okay, and they go all the way to looking at paths at multi-home sites to various traffic paths. So in this chart, if you look at it left to right, you'll see the continuum. People fit at various places and may fit 2 or 3 along this in these particular vendors. And that's interesting because that really says something about the internet from the enterprise's viewpoint. And then when is it monitored? Does a user initiate it? Does an event initiate it? Or is it continuous? And you will find as we walk through these people that some people choose continuous and some say I want an event. Some say the user tells me to go and I say go. How is it monitored? Do you do active probes? Do you do active probes plus TCP synthetic probes? And I'll go through what those are in a moment. Or do you do passive probes, which are the NetFlow and the SNMP to see what's happening? Or do you do some sort of other technology? And there are a couple of interesting technologies in there. Or do you just simply do passive probes? And again, that's just the NetFlow and looking at the traffic. Okay, now you've looked at your metrics. What do you do about evaluating it? Do you say, first of all, you've got to decide when you're going to evaluate. Do you evaluate it when you think you have an event, too much traffic going this way? Maybe like yesterday, 90% of the traffic is going through a particular thing. You say, okay, 90%, now I'm going to monitor this path. Okay, that's one way. The other entirely different way is continuous evaluation. I'm going to look at all the paths that I have in front of me, and I'm going to pick the best one. Well, where are the paths evaluated? Are they evaluated at the box, at the customer site and the vendor? And an interesting thing you'll find is we have both product and services. Some people sell a box that you plunk in, and some people sell a service, and some people sell both. So you might do it at the customer network, at both, if it's both a service and a product, or at the data vendor center. How are the paths evaluated? Now, here's a concept that's really cool. People have maps in this area, smart routing, where there's an internet health map. You know, this is the healthy places to go in your internet. The opposite is just to compare multiple paths through the internet, okay? And there's a mixture of both of it. So let's go through a couple of the monitoring mechanisms, and then I'm going to go through how these guys filled out each of the questionnaire, and you can sort of see the various types of technology. What's neat is once you see the differences, these guys will just describe why. I'm describing what, and they're describing why. Okay, so in the basic active test, you know, if you do an ICMP, you get an ICMP response, and you can get a round trip time, and you can figure out if you lost something. That's our basic ping. Jessica, you once said if you can ping it, it's not dead, and that started in 1987. So I think we've used that a long time. When you send a UDP, you can also do the same thing. You can get a round-trip time, assuming your remote side has a UDP responder. You can also send UDPs with extremely low TTL and find out when it times out. You can also do a synthetic handshake test. One thing is you may send a SYN and get a SYN-ACK back, and that will get you a certain type of timing, or you may go all the way through the HTML transaction, which I've laid out in the slide. Okay, so that's the active test. You're out there doing something in the network and seeing what comes back. Now you look at the passive monitors. You can plug into a span port, you can sometimes plug into an optical flow, or you can look at servers. And all of this data is real interesting. Beyond this simple thing, a couple things that fell out when I talked to everybody is NetVMG really has a lot of interesting things about traffic flows. Opnix has OpScore and some real interesting network health map that you might want to listen to later in the slides. Proficient had some packet train information, and Route Science had the HRTT, if I've spelled it right only, I think, and Sockeye had a lot of things about webs and pulling down things. So those are a few things that I found unique between the people. Well, now you've got the metrics, now you figured out what to measure, and you've got to figure out how do I pick the best route. You measure, the metrics you measure turns into a quality measure once you put your goodness feature. So you've got all these metrics, and some of the art is, how do we say this path is good and that path is bad? It's because each of these people have determined what they consider their goodness function. Now these goodness functions may be run on all of the paths, and you say, this is the goodness threshold. This is the goodness where I say this is the right and true path. Or it may be run on various thresholds. Okay, so now you got the paths and you want to figure out what you do to steer the traffic. Well, first of all, you're getting BGP routes in, probably from 3 different eBGP peers, and you're getting it to the smart routing box. It says, aha, I have picked the best path. I know the right way. So coming back from it comes a BGP internal packet saying, okay, here is a better local pref and a no export. So there are several options in even saying this better BGP route. It can be the local pref is lower, or there's no local pref. It can be this, if there's no local pref, then the ACL list inside each router will be adjusted to say, believe this guy first, because he knows what he's doing. If you have the same prefix, that's great, or you could have a more specific prefix because you wanted to have a /16 turn into 2 /17s, or it's a /24 that you want to install. These are all differences between various vendors, and it's interesting to me as someone who's been in BGP to see these differences come out. The S path can be zeroed or the same, and you may or may not send it to the originator. Now, there's a couple health habits that are really important. The one is set the no export community. All of these guys do it because essentially, remember what they're tuning is they're tuning the exit points inside of an enterprise. I'm sure that's probably inherent from this diagram, but it's well worth echoing that these guys actually are tuning paths within the actual original ISP. Okay, what impact will this actually have on service providers? And I took some of this from some of the marketing literature and then just tried to detune it into reality. Well, what happens is enterprises are building something so they can get better end-to-end performance. If the enterprise is fine, they have an ISP that doesn't work, it may route around it. Complaints may get specific, which is really good in some respect because, you know, I'm sure you're tired of it broke. The pause at the other end it says, what broke? My connection broke, and you go down there. If connections say, instead, you know, this failed at this date with this type of statistics, it'll be easier to debug, but it will be interesting. SLAs may tighten, and enterprises may tune down their over-provisioning. That over-provisioning is not as important to enterprises as just having reliable service. Okay, I think I put up on the website all the questions and details, but this is a synopsis of the questions we asked to each of the vendors as far as being a moderator. What's your product offering? How do you define quality? What tools do you use to measure traffic flow? What type of BGP routing data do you keep? How does your product steer the traffic the right direction, and how does your product interact with the enterprise's other boxes, the routers, the firewalls, the web crashes. You know, pretty soon the enterprise has a rack full of equipment. Okay, so let's just go and look at these guys one by one or in sort of classes. If you notice that the first 4 vendors have a product, okay, and Sakai is a service. The interesting thing is Opnix also is a service. So you'll notice people who have a service tend to have a data center. Everybody changes the IBGP routes, and everybody uses data that I'll call nowcast. Nowcast is data which is pretty much real now. How long that nowcast data is, it's pretty much immediate. What's the definition of immediate? Well, that varies a little. I also put in here something that I found interesting. How long had these guys been looking at BGP or running their actual traffic? You know, what's your time in gray to tell me that this really works? Well, the interesting thing is we run from 9 months with Sakai, although Sakai builds on top of 36 months of Akamai's network map technology, all the way down to Route Sciences 22 and NetDMG, which is 22, Proficient, and Opnix, which have a little over a year. So what's their basic measurement approach? How would I actually look at this? Well, NetDMG takes the span ports and look at the monitoring at each site. It really looks at traffic flows. Opnix has network maps plus local flows plus span ports plus net flows, so it's a combination. Proficient has active flows, probes into the networks, the ping, the TCP, the UDP probes, span ports, net flow, and Route Science has web application monitoring, although it does the active monitoring as well. When requested. I've got the Sakai probes the internet through its various places to make sure the health is there. Okay, so let's look at various measurements. What are they trying to look at? If you look at this, you'll see that everyone wants latency and loss and carrier costs. That's sort of the bottom line. Everybody wants to know what's the round trip time. If I'm losing something, where's the carrier? NetDMG and Proficient and Route Science also look at jitter. You know, what sort of variation, because that will set some applications. And you'd be surprised the number of really legacy applications that might be hanging out. Old SNNA stuff, which we all thought was dead, gone, and buried, may actually be in many enterprises and is significantly impacted by some of the jitter and traffic flow. NetDMG also look at traffic flows. Opnix looks at NAP hops and layer 3. And Route Science and Sakai look at some additional metrics on web statistics on that round trip. The level that they measure in NetDMG can either, or in all these, can either be the prefix or the AS. And again, I think I've gone through some of these unique things. The traffic flow monitor for Opnix, the fact it's both a service and a product, and it can merge the database, and it has 2 unique probes, QA and Discovery probe. Proficient has packet trains, Route Science is HRTT, and Sakai has the Akamai map. So when they come up, how do they actually come up and start to decide what's probing? Well, the interesting thing is that the service people fall out different than the actual product people. If you look at Opnix and Sakai, they're pre-configured to do some tests. That's what you'd expect inside of a service. Everyone will do whatever the user wants because the enterprise is king from their viewpoint. That's what customers usually are. And vendors, if you look at who does vendor-provided stuff, you'll find that Opnix and Proficient and Sakai. Everyone tries to learn from the network, and Opnix and Route Science and Sakai have some external databases which give them some leverage. Okay, now we've gone through what you probed, where you probed, and what's the goodness function. Now here's really fascinating. You can look at some of these things where NetDMG has a function of latency, loss, and cost, and it's a dynamic threshold with customer-defined policy. Opnix uses OpScore, which is a combination of this health map, the active probing, the customer filters, and OpScore is compared for all transit links. Proficient has the user specify the weight of the metrics. Again, this is where the difference of the approach is. Should it be the user? Should it be the health map? Should it be something inside? The quality is compared per path. Again, you're going to notice everybody looks at per path to say, do I go out this path or that path? The Sakai has a path shortfall, which is a latency and the Route Science has an optimization of latency, loss, and jitter, and is constrained by the SMMQ thresholds and a comparison to alternate paths. And again, Sakai also has the path shortfall constrained by cost and goes through various transit providers. Well, we then talked about in the group of all of these, what sort of probes. And again, you'll find in your presentation, which I'm sure most of you are clicking through, watching on your local site, what sort of ping-like things you have. If you notice that ICMP pings and UDP pings, I tried to differentiate between locations which were actively probed and pings with things that are set up by configuration. NetVMG uses ICMP and uses UDP, and you notice it has the customer site, one location, and some key internet sites. Route Science, on the other hand, doesn't automatically probe anything. Excuse me, the people who automatically probe things are NetVMG, Proficient, and Sakai. And people who don't go through and automatically probe using the ping-like approach is Opnix and Route Science. You'll notice that the difference between what you can probe and what you can't probe is really a decision. People decide in the vendors that it's a good thing to probe automatically or not. And again, you have to look at their sort of theory behind there. I think in the interest of time, I will let you go through some of these slides. Again, notice here we have some slight differences between these folks, that you'll have a trace route function from NetVMG, Opnix, and Proficient, some based on UDP and some based on ICMP, but not from Route Science. You should ask yourself while Mike is giving the presentation, why doesn't he take this approach to do trace route? Why ping and not trace route? These questions are, each one of these guys is trying to do a really good job at being responsible about how they look at the network and what they actually monitor. Okay. So again, you'll find that in the trace route probes, the Opnix can do everything as far as configuration, and NetVMG has some things. Data flow monitoring. In the data flow monitoring, you will find that the SNMP queries and the net flow is pretty much what each of these vendors are taking a look at. There is an optical and span ports, the way that people usually get it, and they usually monitor customer routers and end users to see what that traffic goes through the net. Okay, event and quality. Now you've pinged everything, you've figured out how to look at it. When do you do it? When do you evaluate that path? Remember that original diagram. When do you actively set a probe? And when do you have a probe query? Well, it's interesting that everyone does a continuous evaluation, but some people choose to not do an event-based. Okay? If you have an active probe set, again, notice that the service providers automatically send it, and the other people send it in their continuous probing. After an event, note that Route Science doesn't actually send that. So when you decided what you're going to do, how quickly will you do it? Is it user-defined? Most people, except for Route Science, have a user-defined. What's the default? Is it 1 minute? Is it n seconds? Is it 5 minutes? And you'll see where the people vary. And how many, pardon? It's not, okay, good. Mike tells me I'm at the end of time. I'm going to wing through a few more slides after I finish this one. This one's actually probably interesting, that you'll find that people vary in their limits, and I need to get to 2 more slides, and I'll try to get to my time sequence. Everyone pulls BGP routes. Some people pull global routes. Some people pull external databases. Again, you notice the external databases and the global databases are done by service providers, and everyone, Dave Myers asked me, do people look at route views? Only for R&D. Do they look at the route database? Steering, I think I've gone through most of this. The interesting thing is that some people will do it via /24 or policy-based routing or /32. Everyone does it safely by putting the no export community and encouraging the routers. And then the last thing you should look in this is what's the change threshold? Is the damping interval? How often do people reroute? Okay, is it policy-driven? Is it based by the customer? What's the maximum number of BGP updates per second? And what's the damping interval? And I encourage you to look at this sheet and take a look with the guys. Everyone says they do just great with other vendors. Now, I'm going to quickly slip over to the guys, each vendor, where we'll go alphabetically. We will start with NetBMG, Opnix, Go to Proficient, Route Science, and Sakai.
Hi, I'm Jeremy Johnson with NetBMG. I'm not NetBMG. I'd like to start off with a slide that kind of shows what the product does in action. This is basically a graph the kind of graph that you get with the product in the reporting interface. And the notable things here are the top part of the graph shows latency values. There are two providers represented in this graph. The green line represents UUNet, and the purple line represents level 3. The shaded in area actually represents the parts of, or the actual performance that's being experienced at this time. Level 3 in this case is the low-cost provider. Not always the case, but in this case is the low-cost provider. And so we prefer to put traffic on level 3. The heavy black line is a threshold, a latency threshold, that is determined by our software. And when we notice that there are 3 consecutive latency violations, or when we exceed that threshold 3 times consecutively, we make a performance-based route change. So in this case, about a quarter way through the graph, we see that there was a latency violation, and we do a performance-based route change. It goes down to UUNet's link, everything's fine for a while, and once level 3 is able to provide the performance that we need, again, we make a cost-based route change. So this, in sort of a nutshell, is exactly what the product does. We take in input from the operator in terms of cost and in terms of performance. We let the software itself does some magic in terms of determining thresholds if the operator isn't sure what the threshold should be, and also does the probing and also passive analysis of data, of actual user data, in order to determine when actual route changes need to be made. This is a real quick marketing slide. I'll just focus on the middle part of the slide. Basically, the product is made up of 3 components. The first component being the flow collector. This is the measurement component. Second component is the flow director, or that's the component with the smarts in it. It takes input from the measurement side and actually makes decisions. Those decisions are embodied in route changes or route updates via BGP. And finally, the flow view component, which is the representation side of things, which we saw an example of, which is basically representation of what is actually going on with the system. So I'll start off with the flow collector, the measurement component. Basically, there are two ways that NetBMG does measurement. We do active measurement, which is basically a combination of UDP and ICMP. For lack of a better term, everything kind of looks like a trace route to us. We generally send out UDP. We have the option of configuring to send out ICMP as well. But in the default shipping mode, it sends out UDP. We measure basically along all available paths with the active measurement, and this is actually why we chose to do active measurement, because we felt that it was really important to get a sense of what each available path looks like. And in order to do that, one might ask, how do you get these probe packets to go out each individual interface on the router with regular routing making a decision? So what we actually do is we require a little bit of router config up front. For those using Cisco's or where it's most convenient, you can use a VRF configuration bound to .1Q interfaces, or you can also use a PBR setup to force the traffic down each individual pipe. We did that because it was fairly simple to do a one-time setup. It sort of fits with I don't know, best practices in my sense of the term, in that it's a one-time router config, and you're done. These probes, again, measure each individual path. They both measure topology and also performance metrics. Now I have jitter grayed out because probes don't actually measure jitter. Jitter is defined as sort of a as a variance across over time, or a variance in latency over time. So this is actually based on cache data or cache probe data. The other part, and the part that I think is really slick, is the passive analysis. This is a device that basically sits on a span port or a physical tap on a network, and basically snarfs off header information from actual traffic on the network. I think this is important because one of the things that you want to make sure that you're doing in a smart routing box is you don't want to boil the ocean. You don't want to try and fix the entire internet when maybe the customer is only visiting or is only being visited by a small percent of the internet. So we actually look at the real data and the real traffic as it goes on. And basically the passive flow analyzer component, as we call it, reconstructs TCP flows and records statistics like volume and also round trip time. One other thing that's interesting about this is that we take each individual flow is basically a /32. We look at those in terms of /24s. So we take, say, 2 or 3 flows destined for /32s within a /24. We aggregate the latency and volume information and then pass it up. That's so that we can actually get it in terms that a router understands. Of course, we don't want to be doing /32 route announcements all day long. So here's some pictures. I'm going to go through these really quick. Basically, this is sort of the idea of what you can get from active probes. Basically, this here is a representation of seven different providers, and there are 3 lines. The red line being the worst provider at any given time, the green line being the best provider at any time, and the blue line being the median provider at any time. And the point here is that when you do an active probe, you definitely want to be able to measure all of the available paths, because in this situation, you can see that a couple of times there were very large outage spikes. In fact, if I had the opportunity to drill down into this picture a little bit, you'd see that these spikes actually lasted about 6 or 8 hours apiece. And the thing that's really notable about this is that not only was the worst provider terrible, but also the median provider and all providers in between. And so that leaves but it did leave one good path, which is represented by the green line. We wouldn't have been able to see that was available had we not had the active probes. I'm going to go ahead and skip this slide. I think the basic point here is that when we measure these paths, at any given time, we find that there could be a 25 to 40% improvement in performance from the standpoint of latency. I'm going to skip this one too. So what's measured? Basically, we measure based on 3 things, or measure actively based on 3 things. First is an operator-specified list. These are the important sites to the operator, so like your DSL connection at home. And also we measure primarily, or the bulk of the measurements are driven dynamically by the active prefixes on the network. And this is gleaned via NetFlow or via the passive flow analyzer. And something that's interesting about this is that, and it's represented in the graph to the right, is that basically all of the distributions of traffic that we've seen are heavily tailed. In other words, in this graph, for instance, less than 1% of the prefixes that were active at this point were responsible for over 90% of the traffic. And so that's just one way of saying you need to be able to also organize what you're seeing in terms of active prefixes. So we organize those in terms of volume, as portrayed in this graph, or we also organize those in terms of frequency. We also keep a little bit of room in those dynamically created lists for prefixes that are having major performance violations. One other thing that is important here is now how do you define a problem? As I noted earlier, if the operator isn't aware of what a threshold should be, and how could you be aware of what a threshold should be when your traffic is distributed globally to anywhere between tens and hundreds of thousands of prefixes? So what we did is we built a baselining mechanism that's based on process control models. There's actually a couple different process control models that we use, but it basically gets summarized in the black line here on this graph. The black line is representative of what's going on the internet and is our measure or is our metric of goodness. So as you can see in this graph, the entire internet kind of sucked for a while, and so the threshold tracked that. In other words, there was nothing better that could be done. But as soon as some providers were actually offering better performance, the threshold tracks that as well. And we see, again, in the shaded area, we just happen to be on the worst provider in this case, and after three consecutive violations, we switch back to a better provider. And that's based on our notion of a dynamic threshold. Okay. I'm out of time, so I'm going to rush through these really quick. Basically, route insertion is done via BGP. We do use a longer prefix. In most cases, we also have the ability to configure a local preference. Here's some pictures of reports that you can get. And one other thing that Sue had asked us is how many paths is good enough? And we did a study on this from a couple of different angles. One angle being convergence points, or how much diversity is out there given a provider mix. This is actually a long topic to go over, but we do have a white paper on our webpage, so I'd really encourage you to go there and check that out. But the long and the short of it is, if you get the two right ISPs and your traffic is constrained to a certain set of prefixes, 2 is enough. Now, on the other hand, we also did a study with 7 different ISPs, and we found that the more we added, the more lift we got, and that's what this shows. So, of course, the more the better. And just in summary, what the product's been doing, we've been out there for a while in beta trials and actually live customers. Our products have done over 295,000 route changes total, and in one network alone did 44,000 route changes per month, and was able to save approximately 30% in bandwidth costs by using the low-cost provider and least cost routing techniques. So, thanks.
Thank you very much. It should be. You ready? Good. All set. Next is Aaron Britt with Opnics.
Before I start the presentation, I just want to preface the presentation by, kind of paying attention to the IRC channel out there. These really aren't product pitches, guys. I just want everybody to know that these 5 companies, we're all in the same ballpark, that we perceive a problem, and we really are trying to fix it. So throughout the presentations and obviously at the Q&A, if you guys have data to support any type of critique that you want to do or anything else like that, please let us know. That's what we're kind of up here for, is not just to talk about our product, but to really talk about the problem and how we're trying to fix it. And with that, I'm going to skip ahead a couple slides here. Sue's got us on the 12-minute timer here. So just really quickly, I just want to let you know kind of where the Orbit 1000, which is the product that Opnics makes, actually fits in the network. Typically, like all the other vendors, we kind of just hang off of a router in any configuration that's needed. You talk standard BGP to a router, you get routes and you set routes and you probe stuff. Specifically, the stuff that we probe, from the Opnics point of view, we have 2 different types of probes. I'm going to get into what the probes are actually made of and what they do. But on a high level, we have something we call QA probes, which are probes that we send after we've set a route. We think that the route's good. We made some deterministics that say it's good. We keep checking up on it and making sure that the route stays good. The discovery probes are the original UDP probes that we send in order to assess each diverse path to make that decision whether or not that route is better than the original route that we had. The other functions of the CPE device is obviously to set the routes once we actually figure out what the better route is. And Opnix is kind of unique in that we have this idea that we like data housed in a central location. And this fits two sides of the fence. If you're a small enterprise and you can't afford large boxes, you can buy the service. If you're a large enterprise or a small ISP or something with a lot of money, you can buy the whole ball of wax. The idea is we don't want to close off or pigeonhole you into what type of product you need. We're trying to be flexible enough so that it fits your specific environment. How do we become one with the packet? Interesting enough, a lot of you guys probably remember a couple years ago some NANOG posts with some Opnix stuff that hit the web. Basically, we tried to ping in successive ports the entire internet and really got every IDS system in the world mad at us. We were still trying stuff, and we're not afraid to try stuff. So we tried ICMP pinging. We tried TCP ping. That set some more stuff off. I said we tried the Force, but after the last movie, I'm not sure if that's a good thing. And we settle on UDP. And the reason why we settle on UDP is that it's a lower priority. It's not as intrusive. We all use traceroute. It seemed like a pretty good thing to do, and we still think it's a good thing to do. And we did some testing that said, given a certain environment variables, probe stuff over here using TCP, make some decisions. Probe some stuff over here using UDP and make some decisions. And we found that those decisions were almost identical. So we figured, well, it's about a 2% difference. We'll err on the side of safety versus TCP and continue down the path of using the UDP probe. Where do we probe? It's very interesting, the different philosophies of how each vendor has taken this approach. Ours isn't the best. Ours isn't the worst. I think that we all have our reasons. And it's interesting of not just where we probe, but what we probe. If you look up on the list here, we have some ideas of where to get the information of what sites we need to probe. Obviously, there's some sites out there that you can pay to, and they'll say, these are the top 500 trafficked websites. Okay, that sounds like a pretty good deal. What about a route feed from the customers? We found that each customer has an individual viewpoint of the RIB, and so we'll get their specific viewpoint and kind of throw that into the pot. Obviously using traffic flow data, using NetFlow or SNMP to understand where the actual packets are that those routers are forwarding to. And logs, web logs, DNS logs. Not many large ISPs can actually keep web DNS logs, but the more information we have of where your packets are going, the better and smarter we're going to be able to probe to those places. And we're capable of probing the entire RIB, but it doesn't really make sense to. Again, work smarter, not harder. And once we have this big pot or this big list of places to probe, we then use some standard filter lists to figure out what are the smart places to go to. And then we probe there. It's really hard to figure out what to probe to, so we take a network address and add one to it, unless in the configuration you have a more specific to. Again, that's another reason why we picked UDP. And again, we probe multiple prefixes in parallel over diverse paths, using either a /32 method where you set a BGP route, kind of intrusive, kind of add some load to the router. Some enterprises, they allow that, it's their choice. The other way that we would do that would be a policy-based routing with a route map saying, if you match this IP, set it over this carrier, and we use source IPs. Some of the metrics that we gather, again, we're trying to figure out what's the best for each environment. So we're not the smartest people in the world, so we try to, the customer is king, right? So how do we actually get them to understand what is the important places? And once we figured out what the important places are, we have to figure out what metrics are important to them. So we have latency, unreliability, which kind of throws in link unreliability, probe closure, packet loss, and routing loops. Bad hops, it's a list of NAT hops, plus we have this central database where we can mine what are the routers or what points in the internet today are real time, actually adding congestion and latency, and throw those in the list. Layer 3 hops sounds like a piece of marketing had a effect to have layer 3 hops in this, but I have some data later to show you that even though layer 3 hops sounds anecdotal, it really does increase latency the more hops you go down. Not always, but most of the time. And obviously carrier preference. Which one do you prefer to go over? Maybe it's because of your cost, or perhaps you have a better SLA with them or something. And then if you look at the example, I won't get into the numbers because we don't have much time, but we kind of score everything, and the lowest score wins. Like I said before, once we actually set a route and we think it's the best route, we have to keep testing it to make sure that that route stays within tolerance levels. So we have this separate process that we call QA, and we're really just testing the active link. How much time do I have, Sue? 3 or 4 minutes, okay. So we QA the routes. We say, okay, this meets in certain tolerance levels. If it falls out of tolerance a couple times, we'll remove it and try to rediscover and figure out what the best route is after that. Really quickly, again, I told you we have these two pieces, the CPE and this core idea. The core is kind of a scalable cluster of boxes that is scalable in each box of its own, meaning the balancer, its primary job is to communicate with the CPE and send data upstream. If it starts running out of CPUs, you can throw another box of the cluster. Same with the optimizer. All it does is crunch numbers. The view, it pretty much just listens to all the answers the optimizer gives it and keeps it in memory. Obviously, the SQL database. This will give you an idea of the storage opportunities that we have. With one customer turned up, going pretty fast, we store about 4 gigs of data a day. So you can imagine the disk space that we go through. But we actually like having that problem because of the amount of data that we can now analyze and mine later. And obviously, how do you get access to this data? Well, we have this customer portal where you can run custom graphs. All your metrics and weights are visualized. We have something called Route Vision, which is kind of like a visual trace route, but it'll show you each one over each carrier. And obviously, we have the SQL database, which we have 3 types of data. We have transactional data, which is the information being stored that makes the decisions. This warehouse data, which is what the portal accesses. And then we have all the archival data that we keep off to the side for other stuff. Fault tolerance stuff, thought that might be important. Because we're using standard BGP, if our box goes up in smoke, the router just goes back to standard BGP. We have this heartbeat mechanism, both with the CPU devices and with the core, so if things go bad, it knows that. On this database, we have the ability to store all the central configs. I don't know about all you guys, but if you're trying to configure 100 routers, it's really hard sometimes to get all those configs to a central location. TFTP just isn't what it used to be. So we have this idea that we can keep all the configs in a central location. That way we can restore quicker. Obviously, SNMP works, and we're always adding stuff to our MIB. Things to come, things that we're working on currently today, and if you guys have any ideas, that's great. Supporting jumbo frames, dedicated jitter measurements. Even though we have the data to understand what the jitter might be, it's not a dedicated process. Black hole and routing loops. Since we have many customers all storing data into a central location, it's really interesting to see how many routing loops are in the internet at any given time. It's a much higher percentage, and I didn't actually save any of the data to show you, but if you guys get me offline or send me an email, I can kind of share some of that with you. The amount of black holes and routing loops that exist in any one period of time on the internet is a lot larger than I thought. Emulating the TCP slow start algorithm using UDP. Actually having the ability to have UDP probe or TCP probe. Maybe you want to use TCP because you know the endpoints. Some more sniffing. Multicast support, IPv6 support, some more MIB stuff, and I put that in our NEBS compliant, but that's just a joke. There's no way. And here's my contact. Again, this was not meant to be any type of product presentation. It really is just our stab at the technology. We do have some case studies that I didn't have time to show you guys, so if you guys want to email me, I'd be willing to share those and spark up a dialogue, just so you guys understand. I know, so I'm done. And thank you for your time.
Thank you very much, Aaron. Am I not pulling it up? Yes. Next is Robert Bays, the Chief Scientist with Proficient.
Hi, my name is Robert Bays. I'm with Proficient Networks, and I'm going to talk about the new policy for enterprise networking. And I can hear everybody going, oh no, what is that and what's going to do to my network? So what we found is that when we were talking to our customers, both current customers and past customers in previous lives as network engineers at other places, customers were looking to be able to apply complex business policies to their network. And by complex business policies, what we're talking about is primarily lowering operational costs. Most of the customers that we've talked to over the past couple of years drastically over-provision their network, and now their number one mandate coming down from upper management is you need to lower your operational costs. And unfortunately, what that's translating into is they need to be able to lower their costs that they're paying to their providers. But immediately after saying that, they'll turn around and say, oh, well, we also want to optimize network performance. So if you can do both, that would be great. There's a small subset of customers that want a third thing, and that small subset is actually a very technical group of customers who have the resources in-house to be able to do this network engineering that we're talking about manually. But unfortunately, the resources are pretty time-consuming, so they want to be able to free those technical resources to be able to put them on other tasks. Sorry. So based on that information, when we were designing the product, what we decided to do was, first and foremost, that the current technologies, currently BGP, was unable to handle what the enterprises were looking for. And it shouldn't be able to handle what they're looking for. BGP was designed to provide reachability information. It wasn't designed to provide the type of policies that we're talking about. So we needed to define certain data points that could be used to augment the BGP policies as they stand. And those data points that we came up with currently exist as time of day, link cost, path metrics, latency, jitter, and loss. Once those data points have been defined, we can use those data points to apply them to standard engineering tasks that we saw that we were using in our network on a day-to-day basis and that our customers were using in their networks. Those tasks in our product are defined as explicit engineering, metrics engineering, and load sharing. Using these extra data points and applying those data points to a standard engineering task, what we tried to come up with was a basic generic policy. And using this policy, we can the enterprise can define complex business policies, apply them to their network, and the generic business policy works well into defining a system architecture, and that's how we define the box. So basically, the generic business policy is defined as three questions. First, the user has to answer when and how often am I engineering. The when is pretty simple. It's the time of day data set that the user defines. How often is a little bit more complex. We allow the user to define the number of active probes that the box sends out, if the box is sending out active probes for that type of engineering, and how often BGP updates the internal routing table. The combination or the ratio of those two functions allows the user to define an exponential decay algorithm, which also defines how valid previous or history data is. The second question that the user has to define in order to define this complex business policy is where am I engineering to? This is obviously what prefixes the box is engineering for. The prefixes can be defined in one of two ways, either statically using an access list or prefix list type function, or dynamically using net flow information or using Ethernet tap and flow information gathered from that. The third question is obviously what type of engineering am I doing? And on a very basic level, that's the three standard engineering tasks that we've already defined: explicit engineering, metrics engineering, or load sharing. But each of those standard engineering tasks has subpoints that can be defined to tailor them to more specific engineering types or more specific situations. And the reason that we decided to define this generic policy is so that as new engineering tasks come up or as new data points are defined, we simply code them in a module and stick the module into this generic architecture for a system. So with that information defined, with the extra data points that are supplemental to BGP, we can apply those data points to the standard engineering tasks. And the first standard engineering task that we have is something called explicit engineering, which is really nothing more than a route map with a time of day function applied to it. So basically, the box is capable of allowing the user to define a next hop for a given prefix, and the box will check to make sure that that prefix has NLRI for that next hop, and if so, at a given time of day, it will insert the prefix with that next hop and monitor to make sure that NLRI is maintained. One of our customers is currently using this function to route all their VPN traffic over a given provider during business hours. So the next standard engineering function that we have is something called metrics engineering. One of the customers that's using this right now is trying to use metrics engineering to minimize jitter across their providers so that they can optimize the quality on their VoIP traffic. One of the differences that we like to think that we have is that we don't tell the user this is the best path because it has the lowest latency, or this is the best path because we have a standard algorithm that came up with this number that tells you it's the best path. What we like to do is allow the user to say, no, what I really want to minimize for is jitter, or what I really want to minimize for is jitter and loss, and I think that jitter is twice as important as loss, so come up with a way that I can relate that to the system. So how does this metrics engineering work? The first thing that we do is we send hop-limited probes down each path in order to determine the last intermediate system. Once we determine the last intermediate system, we store that information, and all subsequent test packets are sent to an IP address in the prefix that we're testing to, but they're limited on the last intermediate system. So this gives us TE expired responses. This gives us consistent enough results coming from the routers in order to be able to calculate latency, loss, jitter, and also packet trains based on Konstantinos Stavroulis' work at the University of Delaware. I also have cost there. The packets themselves don't give us cost information, but if we know the absolute amount of traffic or the aggregate amount of traffic for a prefix, we're able to say, if I put this prefix on path A, it'll cost me X, and if I put it on path B, it'll cost me Y. Once all these data points are defined, at the BGP update interval, or every time we go out to update the iBGP sessions, we will rank each path or each test in each path using a simple ranking mechanism. Once each test type is ranked using the simple mechanism, the ranks for each test are summed up and then weights are applied. The path with the highest rank then wins, and that's the one that we insert. It's interesting to note that we tried a whole bunch of statistical analysis routines to come up with a better method for choosing the best path, but hindsight being 2020, what we should have realized is that it's impossible to correlate distributions for not only different test types, but even for the same test type across multiple different paths. So it turns out that simple ranking is actually the best way to determine what your path is. Finally, we allow the user to define a variance and a hold time in order to minimize the impact on the iBGP network. The variance says that if path A and path B are within 20% of each other, then don't do anything, leave the status quo. And the hold time says, I've already updated this prefix X number of times over the past Y minutes. Don't do anything because I'd like to stabilize my network. So what we've seen in production is we've seen that for the most part, our enterprise path characteristics are constantly changing, and whether this is due to overloaded links in the enterprise or whether this is due to characteristics inside the ISP itself is dependent on who the enterprise is. But based on the definition that the user provides for the best path function, our box is consistently choosing the best path. What I've got up here is a graph of latency to a given prefix from one of our customers. And I chose this graph because at the end of the graph you can see that the prefix was withdrawn. The red, green, and blue lines are all possible paths and the measurement responses for it. The blue path is a path that doesn't have NLRI for this prefix, and the yellow sub-shading is the path that our box chose, or the response time for the path that our box chose. The final standard engineering task that we have defined right now is something called load sharing. And this is something that we were having to do quite a bit at our previous jobs, and that is we would go into a country where capacity was either very expensive or hard to come by, and in order to be able to get all of our egress traffic out, we would have to buy multiple low-capacity links. The enterprises are seeing the same problem in that they're having to distribute their traffic across these multiple low-capacity links, and BGP is not doing a very good job of it. So their need was that they wanted to be able to distribute this traffic, but they also wanted to be able to minimize cost because that's what their management's telling them to do. So load sharing works by first the user defining what's called a cost schedule, and each peer is capable of having a cost schedule which consists of multiple tiers, and each tier consists of a peak rate in megabits per second, a dollar rate for how much it's going to cost me, a billing type, and a percentage. Once these cost schedules are defined, the box will go out and monitor the routers, and it's capable of calculating how much have I spent right now, and it also calculates what's my estimated cost in the future based on linear regression. Once the cost schedules are defined, the box gathers flow information based on either net flow or an Ethernet tap and aggregates that information into prefixes. The prefixes are then distributed across egress peers based on what the user defines as wanting, or the user-defined egress peers for where the traffic is supposed to go. After a prefix has been placed once, the algorithm is intelligent enough to leave the prefix on that next hop, until the prefix is removed from the algorithm. And load sharing also has something called an AS path variance. By default, the user says, if I'm load sharing this traffic, I don't really care about performance, but AS path variance is a way to kind of minimize the negative performance impact of load sharing, saying that if I have a hop that's 3 AS paths long and I have a hop that's 10 AS paths long, the 10 AS path hop may really not be the same as the 3 AS path hop, and I can delete that 10 AS path hop with a variance function. So the impact that we've seen on the enterprise is that the enterprise has unpredictable costs and capacity, and in trying to minimize their costs, load sharing will actually go out and it will minimize the cost for transmitting a given amount of traffic, but it may actually increase their bill because they may be freeing up resources on what was previously constrained link. Our routing update process is obviously where IBGP peered. We have an inactive route discovery process. We're only going to learn the route over the active BGP session that the router has in its local rib. So we have to go out and each different vendor, we have a method for getting the routes that are in the adjacency rib in. We only take the routes that were learned or locally originated on the router that we're peered to. So in other words, if there's a IBGP route that comes across on a border router, then we'll only use the eBGP routes that are there. If we learn a route using an inactive method, we monitor it, and the configuration interval for monitoring is user defined. We can insert either the entire prefix or a subnet of the prefix, and the subnet can be either a absolute CIDR mask or a relative CIDR mask. So if I have a 16, I want to go down 2 levels. Obviously, our inserted routes are chosen based on local preference, and we only insert routes where necessary. Okay, is that it? Yep. Thanks a lot.
Next is Mike Lund from Route Science. Make sure I've got the right one.
Thank you, Sue. So Sue did a fantastic job of gathering a lot of the information on what exactly we all do in advance, and she's run through that. So I'm just going to deal with 2 of the questions that she put to us about who buys this and why, just a couple of quick slides on that, and then why did we take the particular approach that we took at Route Science. So on the who buys this and why, I don't think there are any particular surprises about this being of interest to enterprise websites and people who host a lot of content. The reasons to use it, I think, are probably pretty self-evident, that it's about a gain in performance, it's about avoidance of all the things that routing protocols don't detect, performance degradations that are really severe. Generally, we're starting to use this term brownout a lot. Routing protocols are pretty good at blackouts, but they have no mechanisms for brownouts. That's what this technology is about. Frankly, yes, a lot of the enterprises are interested in this technology because they can steer to policy constraints, so that means they can spend less money with you guys on their bandwidth. I've got to be honest about the fact that that's a main driver of the economics of what we're doing. One of the things that you can look at across the vendors is what kinds of performance sacrifices do you have to make to get the bandwidth savings, and of course there are operational cost savings. Slightly more interesting from a global IP system point of view, the sort of thing we're supposed to discuss here at NANOG, is this detail of enterprise VPN. You'll see a lot of press releases and activity from the various vendors in this space about VPN. Initial product launches focused mostly on that first point about enterprises facing out to all endpoints, but there's a lot of enterprise interest in VPN, and you all know why, right? Everybody knows that you could save an awful lot of money if you could stop doing private dedicated circuit, frame relay, ATM transit between your major corporate sites. All the corporations are using VPN now for remote access, but they're not using it for site to site. Why not? I think these problems have been discussed in places like this a whole lot. There were security issues, but those have largely been addressed, and there were performance issues. This technology has the possibility of solving those performance problems. Now, I'm not suggesting that I can stand up here and prove that this is finally the peg that's going to release the logjam of corporate VPN traffic onto the internet, but I'd like you to think about the fact that that's one of the things this can enable. I've broken out here a few of the other things we discussed for solving these kinds of problems. You all know that there's a lot of circuit-based stuff still out there. The best effort stuff doesn't work because of the unreliable performance. People don't migrate those critical corporate applications. You can do all the various flavors of end-to-end QoS commitments, but C-circuit based for some of the problems there. You know, this is the debate we always keep trying to avoid so we don't just chew up all our time on it. But smart routing, it's an effective solution today for increasing the performance site to site for corporations. And that's important to an ISP audience because this could be finally the driver of IPVPN deployment for major corporate applications. And we're all waiting for it. We all want it to happen. It would be a good thing if we can finally find the enabler for that. And we believe this technology is it. And of course, several of us have announced service provider customers, so it wouldn't be right to just say this is purely an enterprise technology. If you are a service provider, you can get a lot of brownout reduction benefits. We've had several talks in the last couple of days about, you know, reasons you'd want to collect a lot of net flow data and retune your BGP, and a lot of points have been made there. I don't want to repeat them, but clearly if you run a fabric with a collection of peers, collection of transit links, you need a way to optimize that. You may or may not want to do it in real time with these kinds of tools. You might want to just do it in a reporting fashion. But these tools are effective and useful in service provider environments. There's a much longer discussion about how to deploy them. We don't have time for that right now, but obviously if you're interested in that, any of us would be happy to talk about it. So one of the things we have to talk about in an enterprise context that may be less of a surprise here is whether there in fact is a performance problem at all. This is not, in fact, our research. This is independent stuff from Net Forecast, an analyst organization. But they've taken data from us and from a number of other sources to look at, well, how well does the internet perform? Because a lot of it's really pretty good. And what it comes down to, well, I stole a little bit of Longfellow there about there was a little girl who had a little curl right in the middle of her forehead, and when she was good, she was very good indeed, but when she was bad, she was horrid. That's the state of the internet as experienced by enterprises today. A lot of the time it's pretty good. When it's bad, it's really dreadful, and that is a really big problem. You can't run a good commercial enterprise when faced with that kind of performance. So there is a problem here in need of solution. The actual study that this was done for was looking at various commercial measurement and reporting techniques, and some of those lines over on the far left are illustrating the way that various measurement techniques underreport the severity of this problem, because it's very hard to get visibility. It's very hard to look at the huge volume of data to get a sense of how the internet is performing for you and your application. So our particular take on that problem, stealing a line from Casey, if you've seen that video on measurement. The answer, my friend, lies in measurement. Not a big surprise in this audience, but the way route science looks at this, I'm getting now into the philosophy of why we made the decisions we did, that you can see broken out in Sue's slides about the way that we don't use a lot of trace route, we don't use a lot of automatic probing, because we decided that the edges of the network have a great motivation to optimize, but they also have the power to optimize with their existing traffic. And I went looking around at all the literature of the end-to-end principle. I thought that might be relevant. And I found this particular quote right the way back in, quoted in RFC 1958. I admit I'm being slightly cheeky. It's very slightly out of context. But if I run through it, the function in question, any arbitrary property of a network, can completely and correctly be implemented only with the knowledge and help of the application standing at the endpoints of the communication system. That, in a nutshell, is why route science approaches the performance measurement problem the way we do. Let me unpack that just a little bit. This is a slightly wordy slide, but I want to point out why when you see materials about route science, you see a lot of discussion of web content. The reason we focus on that is not the only thing we do, but we focus on it because HTML is certainly not everything, but it's everywhere. It's very rare these days to find organizations who are not moving HTML around, even if it's in support of some other application. And for sources and sinks of this sort of stuff, there's an awful lot of it to go around. This is very, very useful. And down a couple of bullets, HTML also has some very interesting properties about the way that in a client-server interaction, the server can tell the client where to find things. That's a very nice property of an application, and given that it's ubiquitous, well, then the particular wrinkle that we have for data collection, if you do have HTML in your organization, is we reserve one of the objects in your HTML environment. So when you're serving out content to end users as they come to you, we reserve one of those objects, and we serve that from a specialized web server that we monitor. The nice thing with Spacer Gets is they're really tiny, they're really easy to monitor, and you can see a lot of low-level TCP characteristics out of it. I haven't unpacked a lot of the ways that we actually instrument the web server. I think Sue did a great job of capturing some of that in her slides that sort of looked at how do you measure larger and more complex transactions. I've presented that in other contexts as well. But at heart, what route science is offering as a unique measurement approach is no additional packets. Just use the application, use the end-to-end principle. If you do all this with solicited packets, you can see through firewalls. If you only measure people when they come to talk to you anyway, then you can see what's going on for the real application. You can see why you're spending money on your bandwidth the way you are. So that's philosophically why we approach the problem the way we do. It has all these benefits about we can in real time compare the active and inactive paths. Because we're serving one tiny piece of content, we can afford to do a little bit of experimentation with it. And so we've got some ways to doing that. Like we can unpack that in some other context, but I wanted to emphasize here it allows you to look across all paths, which means you never need to make a change unless you know what impact it's going to have. It gives you a lot of visibility into the benefits and shortcomings of each ISP. We've started getting the telephone calls we've been expecting from ISPs who have customers who are using our technology, getting these kinds of reports out, and they want to know from their ISP why certain problems occurred. Sue referred to this with the references about customer complaints getting more specific. Yeah, that's happening. We're getting phone calls from a number of ISPs who want to discuss what their customers are saying to them. So that increase in visibility is very powerful, but it's also something you need to be aware of. That's one of the reasons we're here to talk at NANOG, because you need to be aware of what enterprises are using to measure ISP performance. And this approach is also useful for saving money. Sue made reference as well to the fact that we don't use a lot of traceroute. I put up sort of philosophically here why we do that. If you have this based on solicited traffic approach, this looking through firewalls approach, there's not a lot of need to go trace routing across the core. So that's one of the reasons we have some blank rows in Sue's tables. It's just a philosophical difference among the vendors, but I would encourage you, if you're trying to make evaluations in the space and figure out what you think of the various approaches, measurement is where you'll see a lot of differences between us, how exactly we go about getting the data. This is just one screenshot of the kind of reports we generate. I referred earlier to the way that ISPs are starting to ask us, where did these enterprises get this data? What they see is things like lists of prefixes, and there's a live web UI for a list that's annotated with BGP information. But the point here was you can use it to gather things like, this has been sorted by the difference in performance between the two providers captured here. So you can identify things like a prefix there at the top, where a single TCP handshake, the speed of that is differing by about 3 seconds based on one hop. So you're standing at the edge of the network, you've got 2 hops, you route the packet this way, you route the packet that way, you get about a 3-second difference in the effective round trip time. That's a fairly substantial difference. That's worth knowing about. You can gather this data, by the way, whether or not you actually allow the device to touch your network. You can just have it sit there and report and gather this sort of stuff so you can look at it and learn about what your network's doing. I do want to reference another thing that's causing our phone to ring and getting us into conversations with a lot of ISPs is we published a study on ISP price performance. There's a URL there. Contact me if you want a copy as well. But what we did was we just gathered a lot of data from some infrastructure. This is all data from last August. We wanted something before September 11. We looked at the BGP load distribution for a bunch of enterprise traffic, and we looked at what we would have done in performance. A lot of enterprises just come to us and say, who's the best ISP? Just tell me that, and then we don't need any of this technology. And our answer is always, well, it's not that simple. Path diversity is what you need. You need to get service from multiple providers and be able to route intelligently between them. Fundamental result being any pair of providers we've found, and we can demonstrate these figures, can perform significantly better than any other pair of providers where you just use BGP for your routing. We'll have more details on BGP after the break. This is my last slide just on fundamentally why you should care about this. If you're an ISP, why should you care about this technology? There is a carrot in all this. And I think it's worth looking at that. It is good for you if people use this technology, or I would claim so. Self-sufficient customers are good customers. They complain less because problems get fixed for them, and maybe we'll get to that in the later session. If you accept my claim that performance is the thing that's keeping that VPN backlog of traffic off the public infrastructure, well, this is the technology that could finally deliver on that much ballyhooed promise. It's about getting your fair share of traffic, not what BGP does. We'll talk about that later as well. Increased ISP diversity. There is a stick. I've already talked about the fact that you get calls from the customers because now they can see things they couldn't see before. So I would encourage you in response to this carrot and this stick to look at this technology, use this technology. It can be applied in ISP networks.
Okay. Thank you very much, Mike. And we missed thanking Robert for his time as well. Thank you very much, Robert, for your presentation. We go lastly to Sakai. We will be running probably about 5 minutes over to 10 minutes over, Susan, into the break, or a few minutes into the break. We will give Brandon his chance to speak, and then we'll hang around for a few minutes and answer questions into the break as a panel. We'll take a shorter break as a panel and then start. So when Brandon is finished, I'll bring us all to order and see if we have any immediate questions. If not, we'll go through the break.
I'll do my best to keep this on time. So first of all, Sockeye Networks is a service. We don't actually sell a piece of hardware or a product. We are a service which has some pretty good benefits to it, especially for enterprises. First of all, it really minimizes the risk, right? Because you don't have to worry about upgrading the hardware, or if Sockeye goes out of business or something like that. You're just in a monthly service contract, and you can, it's usually a year contract, but you can cancel after that. Ease of upgrades, we take care of everything. Ease of configuration, whatever it is, we handle it at our NOC and in our data center. So it's all handled for the customer, so they don't have to go in and screw with these things. Of course, there's a lot of knobs and dials that a customer can turn if they feel so inclined. But first of all, how our solution works as compared to the others. First of all, we have a partnership with Akamai Technologies to do some network topology mapping. And where this is important, of course, it would be best to measure every single address on the internet or something like that, but there's certainly limitations there. First of all, you don't really want to do that because you piss people off. Second of all, there's just too much to test. So you have to have some sort of representative points to test to that represent larger blocks of address space, either prefixes or ASs. So the Akamai technology, since they have their servers scattered throughout the world, have a pretty unique viewpoint on how the internet is composed, on what the actual topology is. They can go out and test the paths to many different destination networks and see where the commonalities over those paths are from many different angles. So the common routers, usually towards the edge, that are common from those different angles, we call core points, because they're core points of the internet. They are representative of those larger blocks of address space at the edge, those prefixes at the edge. So Akamai collects this information for us in the process of doing their normal business, and we get that from them about once a week. We do some processing on that and push it down to what we call the Global Route Appliance, which is a 1U rack-mountable appliance that we put out at our customer sites. That appliance then handles all of the testing for performance reasons out to the internet. There's actually been some kind of FUD out in the marketplace about us saying that Akamai is somehow doing some performance testing for us, and that's just not true. All of the performance testing, all of it, always happens from the Global Route Appliance on the customer's site. And of course that's important because you can never tell what the performance is going to be like for a particular endpoint without testing from that endpoint. Testing from a different angle on the internet isn't going to work. So as I said, we push that data down into these appliances. The appliances then go and do this testing. We support two types of testing, ICMP ping and the HTTP header downloads that Susan mentioned for us. Really, the ICMP ping is quite sufficient for these purposes. Keep in mind, yes, usually the initial reaction is, oh, well, you're pinging routers, that's not really reliable. But keep in mind that we're only looking at the comparative difference between two paths when we ping that router. We don't really care about how long the router itself takes to respond, as long as it's fairly consistent across multiple pings from multiple directions. We then also combine that measurement data with NetFlow data that we collect from customers' transit routers. NetFlow data is used for a couple different reasons. First of all, we can use it just for the visualization that's within our service, and I'll show you a little bit of that a little bit later. But more importantly, we can use that NetFlow data for cost-based routing reasons. When I say cost-based routing, what I mean is the fact that many customers will want to limit how much bandwidth they use on a particular transit connection.
If you can imagine like a T3 where you pay X dollars a month, and for that X dollars a month comes included, say, 5 megabits worth of traffic is a fairly common scheme. Well, if you're already paying for it, you might as well use it. So someone might set their threshold at 5 megabits to say, no matter what happens, try to use up to 5 megabits on this link, but when it gets over 5 megabits, route that traffic over to the second link. So the net flow information we collect over time tells us about how much traffic a particular prefix is using. And that lets us do that cost-based rerouting more efficiently. When we know we want to move 3 megabits from link A to link B, we can go look through the historical list and make a pretty good guess as to what block, what address block we should move that would equal out about 3 megabits. Customers can also add what we call VIPs, very important prefixes. They're just prefixes that a customer can manually configure with some test points so that they don't have to depend entirely on the data that we get from Akamai. It's good if a customer has some really important customers that they want to make sure are always optimized and know their topology, or if it's like another customer VPN kind of site, generally they're going to know exactly what their own topology is. They'll know what the test points are better than anyone else. So once all that data is collected, we calculate what we call a path shortfall measurement, which is a normalized number between 0 and 100, and I think there's a slide on this a little bit later here, that tells the kind of the normalized performance of that destination for that transit link. So that measurement does take into account both latency and loss. Once we compare those numbers and then constrain that with the cost-based routing that we talked about, we will go ahead and insert routes back through IBGP into the customer's edge routers. Now, when we are routing based on AS, we can route based on AS or prefix. When we route based on an entire AS, we do split those routes to more specifics when we send them back to the router. There's a good reason for this, since we want to see exactly what routes that AS is announcing to us. We can't send those exact routes back through IBGP because, of course, that would cause their router to withdraw those routes to us, and then we wouldn't see them anymore, and then we would withdraw them back, and we would end up getting into this spiral of death kind of situation. So we always split the routes when we send them back for AS purposes. When we are doing so strictly prefix-based routing, we actually just send whatever the configured prefix is back through IBGP, because we don't really need to see that coming in through the IBGP table. Remember, we are testing the performance in each of those links, so if that route did fall out of the routing table for a particular transit link, we would detect that. Just a few screenshots of what our software looks like. This is just the initial login screen. You can click through here to go to pretty much wherever you want. A couple of the benefits of the service that we've noticed. I have a graph that'll come up later, but we've seen that the route selection in default BGP for, say, 3 transit links, the percentage of the time that it picks the best link is 30% of the time. So it's really no better than random. And I'll show you that graph in the second section of the presentations. With our service, we've seen that go 90% or better. Lets people take control of 95% burstable billing, mentioned that before, and it really cuts troubleshooting time. I'll show you a couple of the slides where you can really go in and see a lot of the details about what's going on. First of all, this is kind of the main screen that you usually end up kind of sitting on. It looks good on a big NOC monitor. What this shows is the relative path shortfall information for each of those transit links. You see those private AS numbers in there. Those are just in there because we took the screenshot from our lab. But you can see the higher the number, the worse the link is, and we get some nice colors on there. Of course, it'll also show you things like who the preferred link is at the time, the reason we switched it, and when it was last changed. I mentioned path shortfall already. Some details on that are probably important. Latency greater than 1,500 milliseconds is considered loss for us. That is configurable, but we've done a lot of testing and have found that that's kind of the sweet spot for where to measure loss. we can put different weights to different scan points if we feel that a particular point is more representative of a block than another point, and you can weight maybe one at 100 and another one at 50 to say that this one's twice as important to the routing of this block. We do have some pretty sophisticated smoothing algorithms within the selection criteria so that we're not switching things based on background noise in the internet. There's always kind of a low hum of background noise, higher latencies here and there and whatnot, just based on very, 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 very short-lived events, things like, very brief amounts of congestion and that sort of thing. This is the flow data display. On the left, you see the AS number, and you can see like a ranking and a total percentage of the traffic. Just one example of the kind of things that we can show through the software. You can also see the direct latency and loss and the shortfall measurements on a graph. What you can see here, the red line on the graph on the left, this is a latency graph. You can see the red line, that transit link obviously has much higher latency than the rest of the links, and you get the same idea on the graph on the right. You can turn different lines on and off. You can make them thicker, change colors, all those kind of great things. So if you ever want to highlight something that's causing a problem, you can easily do that. This is actually my favorite display screen. This is the link comparison screen. What this shows you is the actual performance of whichever link we've selected at that particular time. So there's like that greenish, bluish green link and that black link, and you can see that we're switching back and forth. We start out on the blue-green one, then switch to the black one, then back to the blue-green one again, and a couple times after that. And you can see the actual performance we experienced while on that link. So this is the actual experience a customer or user would have actually had throughout this time period. And of course, you can go back and look at an entire history up to 30 days of what was changed and when and why. The right column shows the reason that it was switched. You click down into there, you can see things like historical trace routes and other performance measurements throughout the time. And I think I'm out of time. Thank you very much.
Thank you very much. We appreciate each of the speakers talking, and Brandon's interesting slides. Now's a quick time for Q&A, so if we have any burning questions about this whole technology, now's the time to hit the mics, and we'll stay around for 5 minutes and see if anyone's interested in some of the questions. If not, I don't see anyone rushing to the mic right away. We'll get you out to the break, but after the break, we're going to come back and we're going to specifically look at the BGP reasons and the BGP traffic information that these various vendors have collected. So afterwards is all the BGP stats in your life, but we'll start with this question.
Yeah, I wonder if you think that one of your products will affect the other products. If you're widely deployed in the internet, what would be the convergence point? Where will we reach? Maybe there will be oscillations. Do you think it will be a stable situation?
Okay, so I'll let that, does anyone want to pick it up from the panel? I think the question was, let me see if I can restate it, is do you think your products will cause oscillation with each other interacting or oscillation with some other portion of the network? Is that a good restatement?
Yes, they all will jump to a good path. That path will become bad, and you will all jump to another path.
So we might find flow hopping to the good path and then flow hopping off once that path becomes good, is, it becomes the crowded highway approach. Does anyone want to pick that up?
I'll start with that. That's an interesting proposition. We've actually talked about that. It's actually a good problem to have if you think about it. If there are enough boxes out there actually controlling traffic that we're actually bumping into each other, that's actually a good problem. But I would think, you'd have to have hundreds of thousands of deployments to see that. Directly, I don't think that we actually run into that on the other side of the enterprise, where there's enough bake-offs out there to make all of us sick of baking. But we've never really, I would say that most of our techniques are pretty separate. When looked as a whole, there are certain things that are shared, but we don't really hit each other on one side of the enterprise. And if we're actually influencing traffic on the other side, I'm not really sure how to even guess at when that will happen, if it will ever happen.
This is a very good question. There was a fair bit of discussion of it actually in the bar last night. And one of the things we discussed there that I can repeat here, we specifically designed around this problem about, if these things do take over, you have to worry a little about what the definition of a word like convergence means if it's about flow movement rather than route movement, because the outside world doesn't see the routes change. But the techniques that you can use include not jumping to the best path. Now, I know that sounds counterintuitive in this context, but one of the best answers is just don't go to the best path. Set a tolerance of what you consider good enough. So this is one of the notions we have phrased as winner set width. So you establish, okay, any path within this tolerance of the best I can see will be good enough. And if the path I'm on lies in that range, don't move, because you don't want unnecessary churn. There's no point moving from 41 milliseconds to 39 milliseconds. And everybody up here has thresholds of this nature. I don't know if we all agree on the other principle that we have, though, which is specifically random selection among the members of the winner set. And the reason we go uniformly randomly and don't attempt to tilt the winner set selection is precisely for these problems of, okay, if I have one pointing out here at you and you have one pointing here at me, will we just hop together to the same paths? We deliberately try to avoid that. And you obviously, if it is causing a problem, one of the ways to back off is widen the threshold of what constitutes good enough and then keep randomizing over that larger set. So there are constraints you can build into these products. We have them. I think other guys up here have them too.
Next question? Or wait, Robert or Brendan or Jeremy? Anybody else? Covered. We're covered. Okay, next.
Yeah, follow-up to the old question is how often do these route changes occur? And while you make these route changes, would there not be IBGP instability? Or in other words, there would be exchanges within IBGP, and if these occur very often, wouldn't you start seeing a risk of more IBGP instability type traffic?
I'll take a quick swing at that one too. So enterprise environments are very different from service provider environments, as I described earlier. It is remarkable how many enterprises have isolated islands with two routers in them. When you're in that environment, your convergence properties are a little easier to compute. So all these products, I believe, from one of Sue's slides, I wasn't sure about this, but her collected information appears to indicate that we all have variable rate settings so that you can figure out what rate you want to move at. Nobody, I believe, is in the business of restating the complete rib. We're all in the business of identifying a specific prefix and changing that one prefix. We may vary slightly in the rates at which that occurs, but the configurable rates out of most of the products are pretty high, but the effective rate of change in the data tends to only go at, change per couple of seconds, change per couple of minutes in most of the real-world deployments. I don't know if people are sort of roughly in line with that from real-world experience. We have systems which on a test bench can go a lot faster than that, but in the real world, more than two changes in a second would be a very unusual event.
Is this on? There we go. I just wanted to add to what Mike said is that most of the defaults on our product specifically, and maybe everybody else's up here, are very, very, very conservative. Our defaults for updates are like 15-minute defaults, not anywhere near minutes or seconds. And that's what really we recommend that our customers do.
And I'd also like to add, I'm not sure about the other products up here, but we do also have a dampening control as well as historical smoothing to keep things from oscillating and bumping around real fast. So that plays directly into that as well.
And I think on the slide I have remembered to put up on this, I've indicated some of the damping thresholds that everyone went through. They all do have a reroute threshold and a maximum. Some of them have even a maximum number of BGP updates you can send the routers. So I think it's a summation I can, after reviewing everybody's presentations, that there is actually some significant care taken to making sure they don't do the flood and switch approach. Next question.
Louis from Equinix. For those of you doing active probes, how often are you seeing complaints from those who you're probing and don't understand the type of traffic you're using to probe them?
I can answer that question. We started out by doing ping packets, and we got a lot of responses from firewalls, from IDSs. When we switched over to TE, to expired TTL packets, we I've run 2 scans on the entire internet so far, and out of those 2 scans, I've gotten 2 emails from complaints from companies. So most people don't see the TE packets because they don't go in and look at their counters on their routers. And if they don't see them, they're not going to complain.
We're going to pick up the smart routing panel with BGP issues that smart routing figures out on. This is where you get your eye candy. That's the statistics forever. There are some of us who like BGP enough to have stayed with it for many moons or years. So, here are the issues that BGP is looking at. What percentage of time does BGP pick the best route? What BGP policy does the enterprise use to pick the best route? As you noticed, I said there was either no BGP usage in the earlier talk or lots of BGP policy in enterprises. What BGP tie-breaking is used to select the route, and why doesn't BGP break the next pass? Are there problems? Where are the last question is, where are there problems in the internet? Is it at the edge of the enterprise, in the enterprise circuits? Is it in the tier 1 providers' interior problems? Is there one of the problems that Danny McPherson, who chaired a panel yesterday, wrote an RFC on with a cast of wonderful cohorts, was the IBGP convergence problem, oscillation. Oh, I'm not projecting. Aha. Yes, I'm sorry, thank you. Now you can read the questions. And what impact does MPBGP have on enterprise BGP? And what we found out is there's really no substantial MPBGP in enterprise. There is some VPNs, but we're just not seeing that. So that question, which was on the original questionnaire, went away. So, again, as Mike mentioned in our questions, the routing policy, those who use policy beat it up, just like any other good, strong user. Those who don't use policy use tie-breaking, and there are 2 common topologies. 2 routers, 1 link each. Sometimes this grows up to about 1 to 8 links. Second common topology is 4 to 6 routers with about 5 links per router. Okay, so those are the 2 common topologies. Unlike all the other things, they really sort of break down into that 2 pieces. Okay, so look at BGP route versus traffic performance. And I asked this question of each one of the panelists, and they graciously went back, scratched their heads, and gave me at least some answer, and they'll explain some of these. Okay, NetBMG said, what percentage of the time does BGP have the best route? 30%, but it depends on provider's traffic. What percentage of the time does NetBMG pick the best route? And you'll see we have run between 90 and 95% on all of these. NetBMG said 95%. And if BGP goes wrong, how wrong? Well, the long term is only slightly wrong, but as you noticed in some of the graphs of those peaks and some of the brownouts, BGP does great on some things, but not brownouts. So those guys have been discussing brownouts, or those short-term orders of effect can be dramatic. And BGP doesn't always detect it. That's part of our distance vector, or is that part of something else? That's what these statistics will go into. OpsNet next said between 30 and 70%, and how often does it pick it? Better than BGP. And BGP is usually wrong enough to try to change. And so you'll find out why they say these things in their presentations. Proficient says, what percentage of time does BGP have the best route? It really is dependent on how business policy, and I think you looked at how Robert described all the business policy and is in detail. Robert's detail on all of his presentations was really good to tell you exactly how he actually works on the policy, how much time they feel they do, about 100%, and it depends on the business policy. Route Science and Sockeye had what percentage of BGP had the best route. They said if you have n links, 1 over the n times is the number of times BGP will do it. So if you have 3 links, a third of the time, which reference the 30%, the rest. You can see why in our topologies those answers sort of match each other. What percentage does the vendor pick the best path? Route Science feels 100%, Sockeye feels 90%. Again, look at their statistics and ask them questions why they vary, because I thought that was neat. And Route Science felt if BGP is wrong, it was a factor of 2. And I've seen some of the statistics behind that in the ISMA presentation, in the ISMA conference, which I think anyone who can reference KC or talk to the ISMA conference, that's a really good set of statistics that I've seen. And Sakai said it was highly variable if BGP is wrong. Again, the reason is why do we see these differences? Okay, then I asked the next question. Okay, so we're in tie breaking. What happens next? Well, again, most people felt that most enterprises, not all, but most use no BGP policy. The AS path length, is it the tiebreaker? And then I walk through and this is where you're suffering because I actually have been working on the BGP spec along with Yakov. I went through the tiebreakers based on the BGP spec in order of tie-breaking in the document. So do you hit the ASPath tiebreaker, or do you hit the lowest origin MED, eBGP, iBGP, or router ID? NetBMG felt a few hit the ASPath length. Opnix thought most. Proficient thought few. Route Science said less than 50%, and Sakai said few. So we hear the ASPath length, which I again reference some of the CADA statistics as to differences in path length. What's the average path length? What's the difference? Why are we seeing it? That's an interesting question, that the statistics that we have, do we really know all the details? No one felt that lowest origin was being held. MED is very seldomly seen inside of enterprises, which is another thing when you see MED inside of ISPs. And then eBGP versus iBGP, NetBMG, Proficient, and Route Science felt that was the tiebreaker that got hit first there, and then iBGP shortest path was found by NetBMG and Proficient and Sakai, and router ID. If you get down to router ID, it's as good as 50%. We had to come down with some sort of tiebreaker in the end. Okay, where do problems exist in the internet? Well, everyone checked carriers, and we note that there's a financial, as I think the phrase is, disincentive, meaning people don't pay to make sure you hand your business over to your competitor if you're a carrier. So I think we found that as a pretty strong thing. Do we see iBGP convergence in carriers? Now, people thought we saw short-lived small, or they saw iBGP convergence except for Proficient. I actually did an informal survey you saw inside the NANOG mailing list and got maybe 12 or 15 responses. It might have been weighted by those people who cared to respond, actually had iBGP problems, but we saw iBGP problems that people were noting in the ISPs, that is the iBGP failure to converge that Danny McPherson references in his draft. That was actually being found, and the way people were correcting it is they were fixing their topologies, which is an interesting problem there. So people saw it. If the topologies went out of realm, or if there's some risk connection, they saw the problem reoccurring in short pieces. So that seems to match the two set of statistics. I would like to see more information about that to see if we need to think further about that in BGP. I suspect that my interest in all of this has to do with the fact that I co-chair the IDR group. The carriers, other than convergence, are also seeing problems, which means there are flow problems, stuck links, or something. And again, if you listen to your last presentations, people gave you hints as to what they thought might be going on. This is all based on the active probings or passive probings that they're doing. They felt, NetBMG, Opnix, and Route Science felt that the edges also had problems. I think you'll see that Opnix, Proficient, Route Science, and Sakai actually felt the NAP or exchange points, and everyone but Proficient felt like there were some key sites, and I may not have asked Robert the right question, so he may tell us later that yes, key sites have problems as well. But I think what you see is there are problems in lots of places, which was indeed the surprise for me when I actually looked into the statistics. I expected between carriers, iBGP convergence, some congested links, but I didn't expect all that we have. So I put up the vendor presentations, their email addresses. I've had enough queries for people who wanted to ask questions, get statistics. I will put this up at the end while we're in Q&A so that you can copy down their email addresses. This is a fascinating, the BGP statistics is a fascinating hobby for all of us and also part of our businesses. So I think if you want to ask questions, please fire ahead. With that, I'm going to go into the everybody's statistics. I'm going to start again with Jeremy.
Hi. So basically, the notion here, and I think the notion that we're all fairly comfortable with, is that BGP is really a reachability protocol. There are some policy knobs that are supported, but they're fairly coarse. You can kind of imagine from an ISP perspective, there's a lot of aggregation going on, and that's a good thing in the core. It's not necessarily a good thing at the edge, where you see the ultimate aggregation going on in that a lot of enterprises use the default route and AS path prepending as well. So the policies that you usually see in the enterprise are sort of, I'm going to use this link until it fails, and that's that. So there, in terms of ISP issues, I'll go back and say, that aggregation is good for the core, but it's not necessarily in the best interest of the enterprise, because aggregation of routes hides a lot of topology. I've got a graph that kind of illustrates that, and also peering. Peering, it's sort of the old peering politics debate, and we all know that pretty well. So, infrastructure and aggregation. This is a graph that we took on a /20 from our passive flow analyzer, and what we see are two distinct bands in RTT. This is very consistent across all prefixes that we look at, not necessarily two bands, but n bands. And what we've noticed is that in general, these n bands can be described in two terms. Either, since the passive flow analyzer does measure end-to-end and actual traffic, we do see the effects of dial-up. So sometimes you see a higher band just due to dial-up versus broadband, and in a lot of other cases, it's due to the fact that these prefixes or smaller subnets within this aggregate are geographically distributed such that round-trip time is going to vary. So I think this is a good proof that there actually are better paths out there hiding within these aggregates. I'll talk about stability for a second. One of the questions that Sue and I talked about for quite a while actually was how long do these pathologies exist? And I wouldn't necessarily characterize what I'm showing in these graphs as pathologies, but it does show that there is variance, even though sometimes slight, fairly regularly. So this is a graph of a single prefix, again using our PFA, over a few different service providers, and you can see that the round trip time, so actually the graph is showing the minimum round trip time observed. What we're looking for there in terms of the minimum is that we've noticed that the minimum values are fairly stable, and so if we do see a change in minimum, we can actually make an assertion that the topology has changed either physically or logically. And so in a lot of cases here you see things moving back and forth. And these aren't happening on the sort of bimodal or, daily kind of peaks and troughs. So these aren't actually a function of latency due to congestion. These are actually due to paths being moved around. Okay. Another point that I'd like to make is that in our studies, we found that no single provider can provide the best path all the time, and also no single provider is the worst path all the time. So this is another one of those composite graphs where there are 7 ISPs represented here. The red line represents the worst performing ISP in terms of latency, and the green line represents the best performing ISP in terms of latency. And what we see is that for the best providers, the bar charts on the left is the relative distributions of providers as they are the best, and on the right side is the relative distribution of providers as they are the worst. And as you can see, it's kind of evenly distributed. So everyone's good some of the time, and everyone's bad some of the time. And finally, I'd like to talk about one other thing, and that is that we don't always in terms of smart routing, we don't always just focus on when there's a spike or when there's a big problem. In fact, a lot of times, and in fact most of the times, the paths that we choose are based on other metrics such as diversity, and we use things like the traceroute data in order to discover diversity, and that's the primary purpose of using something like a traceroute. In terms of measuring performance, we really try to rely on the passive flow analyzer to give us a heads up as to what's really going on out there. And finally, just a little slide in case folks out there are wondering, how many people are multi-home. This is actually easy to come up with, but via the BGP table, there's some interesting stats. About 5,000 enterprises out there with two ISPs. And notably, I saw there are a couple out there that are greater than 15, but not worth mentioning. So, thanks.
Thank you very much, Jeremy. And next will be Aaron. Did I get your right slides? Yeah, you're right.
Yeah. Remember earlier I was talking about how we have this central database. One of the things that we try to do at Opnix is not really fight against BGP too often. The argument that BGP is wrong is kind of a moot point. It's as wrong as you want it to be, it's as right as you want it to be. What we really try to do is compare carriers against carriers, or upstreams against upstreams. You have two links, which one's better? I'm not really worried about which one BGP is picking. It could be right, it could be wrong. What I'm really worried about is am I picking their best route, regardless of what BGP would pick. And that argument is probably pretty true against all the vendors that are up here. So rather than try to spend more time on why is BGP always wrong, I thought I'd just give you a couple of pieces of eye candy of some of the data we're able to extrapolate out of this database that we have of the probes that we're sending from multiple locations. I thought one of the things that might be interesting is something as an engineer I'm always wondering about, which is how does layer 3 hops really affect latency? You have MPLS, you have VPN tunnels, you have all these ideas of how to cover up layer 3 hops. But ultimately, do layer 3 hops really directly correlate to latency? So this is actually a 30-day summary of some data that we've collected that kind of shows on a TTL average. And if you notice on the graph there, it's kind of interesting that sure enough, which makes common sense, as the hop count goes up, so does latency. But what was interesting to me was that it was a pretty uniform line. I thought it would be more jagged perhaps, or even not as obvious as it does seem. So that's interesting. Another thing that was interesting to me was how many, from a specific endpoint, some A user or B user out there, how many hops away is an endpoint? How many hop away is that server? How many hops away is that NTP server, that mail server? Honestly, how many hops is each endpoint away from other endpoints? And this is also kind of interesting. 14 seems to be the magic number of where from A point to another A point, how many hops away it is, given all the different data points that we're monitoring. We don't have as many data points as Akamai and Sockeye do, but it is interesting to look at this graph that shows from hops 3, which was interesting, meaning I'm probably hitting a lot of fiber tunnels and hitting routers on the other side of those, which means only 3 hops away. But then if you look at the graph, it kind of like does show up going to 14 hops, and then it starts to trickle down. And I didn't go anything past 21, just due to the fact it was such a low amount. There's this myth out there that high latency, and there's a lot of hops out there with 30 hop counts. With the amount of data that we're keeping, terabytes and terabytes of it, it actually shows on average that might not necessarily be the case. Some other questions that we're trying to ask ourselves is, like I said, is there a direct correlation between hops and latency? Hop count is anecdotal, but the numbers are quite convincing that yes, it is directly related. But layer 3 hops is a logical thing, right? Physical hops is probably what we're talking about. And how do you measure that? How accurate is UDP versus TCP? There's a myth out there that TCP is a lot better. And it probably is due to some of the characteristics you can get from TCP versus UDP. But what really is the difference? And how can you get UDP to do some interesting stuff like emulate the TCP slow start algorithm and some other things to use this protocol that, though it isn't as robust as TCP, is still pretty widely used and it's a lot less intrusive out there. And a big one that we're really trying to answer is how much does asymmetrical routing play a part in the world of suboptimal routing? We have some deployments in the Internet 2 Abilene backbone, which their primary concern actually is asymmetrical routing. They have this Internet 2 stuff that's supposed to stay on net with Internet 2. I'm almost done. And so it's interesting, it's actually higher, about 26 to 27% of their routes, which should always stay on the Abilene backbone, don't. So that's human error, right? That somebody's actually misconfigured something somewhere. So how much of these human errors can we actually sort out and find out through asymmetrical routing? And obviously the last one, which is an interesting problem to quander, is net flow stats and other things. On average, a router is only forwarding packets to 10% of the global RIP, so to speak. Yet our routing tables are 110,000 plus. It seems that doesn't make much sense. I'm only going to 10%, but I always have this routing table. It's 110. I know we've all talked about it. I'm not really sure what to do about that yet, but we're still counting packets and trying to figure that out. And I'll turn that back over to Sue.
Thank you very much, Aaron. That number of 10% is very interesting because when we were starting with the NSFnet, Ben Lachanoil did some original flow stats on the NSFnet in 1987, 1989, and found the same 10% numbers. That 10% of the destinations were actually done that way. It's a fascinating piece. Next is going to be Robert, and I think, Robert, I've got to find the slide.
So what is the deciding factor in BGP in our customers' networks? Based on the research that we've done, the biggest conclusion that we've come up with is that there's not really an easy algorithm to define what BGP chooses and where BGP chooses it and what's the best path. Some example statistics or some statistics that are pretty relative across all of the customers that we've seen. I've put up, for example, on the border routers, mostly AS path length isn't chosen. The customers that we're seeing have providers that are of equal stature and AS path length isn't actually a factor. On their border routers, it's usually a determination choice between external BGP and internal BGP or IGP and router ID. But when you move to the core routers, the IGP and router ID start to take over. Policies usually accounts for about 20% of the routing choices in networks where the policy has been applied. Usually policy is in relation to direct problems that the enterprise is seeing. So for example, if the enterprise has an issue with one of its customers, it'll go in and put a policy to implement BGP changes specifically for that customer. The reason that we see the policies not being used in most enterprise networks is one of two reasons. Either lack of expertise on the part of the enterprise, they simply don't have the resources or they don't have the skills in-house to be able to do it, or the inability to do what they want to with BGP, which isn't necessarily a bad thing. BGP issues, what needs to be changed? I had a real problem when Sue initially read these questions to me because in the media and in past presentations that we've all given, it seems like BGP is getting a really bad rap, and people are saying that BGP doesn't make the best path choice. The first thing is that the enterprise is really interested in finding long-term path trends or recognizing problems as they exist. They don't really care if it's in the middle mile, they don't care if it's in the exchanges. What they care about is getting their traffic to their clients. So if we can provide the enterprise with a way to recognize that, it would go a long way to solving their problems. The second point is that BGP usually in and of itself doesn't make bad decisions. BGP was designed to be a reachability protocol. It wasn't designed to do best path choices. And to the extent that it is a reachability protocol, it does an amazing job at what it's supposed to do. I think it's a testament to the people who designed the protocol, who implemented the protocol, and to some of the people who actually configured the protocol that the internet works in the way it does. What determines a bad path varies depending on what the enterprise is looking for. The enterprise may be looking for lowest latency, in which case bad path would be a high latency path, and BGP can actually choose that. But the enterprise may not care about latency. The enterprise may care about finding the ADR for a path using packet trains, or the enterprise may care about jitter. So I can't, at Proficient, we say that you can't blanketly say that BGP finds bad paths or chooses bad paths, because bad path is in and of itself a relative term that needs to be defined by each individual enterprise. Therefore, you can't come up with a single algorithm that defines bad path across all enterprises. The biggest problem really is a lack of customer understanding about how BGP works. If the enterprises were capable of providing a standard set of policies to the, or if the, excuse me, the ISPs were capable of providing a standard set of policies to the enterprises, it would probably go a lot further to solving some of the BGP issues that you see with your customers. Standard policies such as standardized meds that they can see, or standardized communities that they can use to implement their prefixes back into your network, or even something as simple as what prefixes you'll accept and what prefixes your neighbor will accept. The last thing that we think at Proficient is that what we really need to do is give the enterprise the tools to audit what they can't directly control, and in giving them these tools that they can make their own decisions external to the ISPs. It's really educationally interesting and exciting to go out and solve big IBGP problems inside carrier networks, between carrier networks, but the real fundamental issue here is that the enterprises need to be able to control something, and giving the enterprises the tools to do this are what we need to be looking at from this space specifically, not denigrating that BGP is bad or good. So, thanks.
Thank you very much, Robert. And I really, even though I asked these hard questions of what BGP was broken, it's really good to see some of the answers that BGP is just what it is, a reachability protocol. And last, I think I've got you. Okay.
Okay, yeah. So we're running over enough, and I do want to make sure we have some time for questions, so I'm probably just going to try and give a guided tour of what to look at when you have a few more seconds to stare at some of these graphs. Let me get through this as quickly as I can. On BGP, I only have one slide. I'm incorporating by reference. There's a whole other slide deck that I presented at ISMA late last year on comparing BGP to random routing. Do take a look. There's a URL there. This graphic is sort of the greatest hit of the presentation. What it's showing is for a number of different scenarios. The blue line, the upper line, is a fairly obvious theoretical distribution. If you chose prefix routes randomly, you would get, with two choices, 50% of them right. With three choices, a third of them right. That's the blue line. The line below it is the observed ability of BGP to detect performance paths. Now, this is of no surprise in this audience. It's substantially a surprise to a lot of enterprises. They think they are getting some kind of performance incorporated into their routing today. And I use this just to show them that, well, BGP is better than chance, about that much. So take a look at the figures, and I break out how all that works in that URL. From there, I have a couple of other just general pictures of this technology working. I wanted to run through them just for talking points for Q&A. There's a lot of directions I can take this, but it's going from raw data observed at the top across 4 different ISPs. This is a single prefix, right? So out of the entire RIB, I'm just picking one prefix. It's a fairly large one with a fairly large data rate in the deployment this data is taken from. I'm just showing one GMT day. So I've used East Coast time along the bottom. This is actually an East Coast site. You can see right in the middle of the graph, everything's fine. All 4 ISPs have no problems. During the business day, all hell breaks loose. The unfortunate part here is the red X's are indicating the owner of this address space. This is one of those things about the claims around on-net performance, that on-net should always be the right answer, right? That's built into BGP as an assumption, use shortest AS path. But, of course, in practice, there have to be times when that's not the right choice. Here's a nice clean one where during a business day, you can get to ISP A's address space by far better routes than handing the packet to ISP A. And this just breaks out how it works. I also wanted to have this slide for chart number 3 there. There was the question about how often do updates get sent. This is a very busy prefix, you know, the zips law shape where there are some prefixes that really dominate. This is one of the ones that typically dominates in the real world. It's full of active end users. And for this prefix in one day, we send 10 NLRI statements to the edge routers in 24 hours to get the job done, to make the difference between the two quality curves at the bottom. I believe I may have defined some of the quantities graphs here a little more accurately in that other paper, so I want to keep moving. I have just a quick animation here of a real event. This one actually from an ISP, not from a website. We're looking at the top 200 roughly prefixes. and it's just an illustration of the way the BGP distribution, the middle pie chart, doesn't shift during the event. And of course, we wouldn't expect it to. We know it's a connectivity protocol, but this was an event that occurred. It's a performance brownout. And what you see is the green chunk over there on the left, the brighter chunk, the share that one of the ISPs gets under a performance distribution is relatively stable at 10%. It's been stable up to this point. An event occurs. The ISP in this case didn't actually know about it until later. They went back to look through the logs on the box to figure out what had actually happened, and they went through exactly these graphs. They found out T-minus 0, something bad happened. You see the green chunk disappears, but it doesn't completely disappear. That's one of the nice things about an automatic tool, right? As an operator, you know something comes out on one of the, the IRC line or on the NANOG list about ISP X is having a problem, and you have to assess, do I shut the line off or not? You know if you shut it off, you're going to lose connectivity to some prefixes that you would really prefer to keep there. What you can do with this kind of technology is isolate those prefixes. So there are actually still, of the top 200, 3 prefixes are left behind while this ISP is having a problem. An hour later, I really don't have time to expand on all the numbers. An hour later, pages have gone off. The degree of improvement that we quote is decreasing because what appears to have happened is an internal fiber cut-like event, an IGP failure, no BGP propagation at all. And pages have gone off, people are starting to route traffic around, the congestion's getting less bad, and you can see that in some of these numbers, but we're still not adding any prefixes back. At T plus 2 hours, it's beginning to take effect. They're back up to 14 of the top 200 prefixes. By 4 hours after the event, we're back to steady state. So there's a big bump in the road, and this kind of technology can insulate your end users from that. So obviously that's what the technology is about. I just wanted to show you a real example from a real ISP of this happening. There's more details here, including some on-net prefixes, quoting degree of speed up. I leave that if you are interested in looking at iCharts on the web. This is my final slide just to look at, well, okay, fine, so you can tune the BGP all you want, you can make all the difference in the network that you want, but does it actually work for an application? This is not our data, it's data from one of our users, and it's their own application monitoring. The red curve is the day before they turn the box on, the blue curve is the day after, and the net point being it moves left, right? It's just a very straightforward observation with somebody else's tools that their very well-tuned network with a complex application running it, the application still gets observably substantially faster. There's something like a 50% decrease in the median response time of the application. I'm sorry I can't spend more time going over this, but I'd rather get to Q&A.
And lastly, we have Brandon.
Yeah, so this is titled BGP issues, but the real issue isn't BGP itself. The real issue is network performance and how it varies and how it changes over time. These are just kind of some stats that we found that are somewhat interesting. We see greater than or 20 millisecond increased latency events 18% of the time as measured from a baseline, which just kind of plays into the whole variance and performance point. And studies have shown things like 100 milliseconds of latency can show a response of like 8.2 second transaction by 80%, 14.9 seconds. I mean, that's a particular example, but I think everyone's convinced that in this crowd certainly that latency certainly affects application performance. More importantly is how events occur and what they look like. And a lot of this data actually is fairly similar to Michael's. So we're all kind of observing the same thing, which I think kind of puts some credibility to it, I guess. But you can see like some events that last for a long time, some events have really large performance differences, and the best transit connection for a particular destination can change quite frequently. So here's the percentage of the time that we found that BGP was selecting the best route. Actually, in our cases, compared to the data that Route Science collected, we have actually found the BGP performs slightly worse than average. So I don't know the details of your testing, but yeah, that's what I was going to say. So there may not actually be any real reason to expect that BGP does anything other than random selection. when it all comes down to it at a typical enterprise. This is with 3 transit providers, of course, and we've defined a suboptimal route as a route that's at least 20% worse in latency or packet loss than its competing routes. And this is just kind of shows what our results were after turning on our optimization service. I don't know why that's moving on its own. But the reason it's not completely 100% is because we do some dampening and those sort of processes, so we're not always moving on any performance difference. We're moving only when it's an important performance difference. BGP picks the wrong path. This is just an example of that. It's kind of hard to tell in the colors up there, I think, but kind of the pinkish line on the top was the path that BGP chose, while the blue line on the bottom was what our optimization service picked. It's kind of hard to see the blue line, but it's right in there with the mess of all the other lines. Just another example of that. You know, again, everyone in this crowd, I'm sure, is convinced of this, but when you bring this into an enterprise-type environment who think that BGP is just the answer to everything, they're shocked by this. They can't believe that BGP wouldn't always be picking the absolute best path all the time. And there's just one more example of that. Also, what's interesting is that it doesn't really matter as far as number of outages and length of outages on which provider you're on. It's kind of surprising to note that among the different providers that we tested, whether you're talking about 5-minute degradation events or 2 to 4 or 4-hour degradation events, there's not a significant difference. And this is probably because it's not those immediate upstream providers that are having the problem. It's because the problem is somewhere out in the net, and that we can route around it, not necessarily by routing around just that upstream U.S. provider, but routing around some other event that's going on somewhere else in the path. And I'll let you folks study those graphs in more detail, and hopefully we can go to questions, I guess.
Yeah, we're to questions. Thank you very much for all the panelists. This is very interesting. Okay, now we've reached the Q&A moment, and come on up and ask any of these guys on the questions. We'll take the first one.
Yeah, when I make BGP advertisements, that is based upon how I want traffic to come to me. If you guys make those choices, you're no longer listening to what I'm asking you to do. Is there a solution to that?
Specifically for our product, we don't make advertisements unless there's an LRI to match. So if we get an LRI, then we get it from you somehow. So we're not sending traffic out of an interface where we're not seeing your advertisement.
So if you're an enterprise and you're prepending to your ISPs are propagating those prepends to the other enterprise on the other end. If I send a packet to UUNet and you're prepending to UUNet, it will still go via Sprint if you are preferring Sprint. So what we're taking advantage of here is the path diversity in that the enterprises that are buying our products are buying full transit from these providers, and they have the choice to be able to send that packet down one ISP or another. It does not necessarily mean that your prepend is not going to be listened to.
If I could ask Randy to defer for 1 second. It would be slightly easier with the whiteboard, I think, but what we found analyzing problems like that is you can break it into 2 cases. Are you trying to influence an immediate customer or peer of yours, or are you trying to influence somebody 2 or more away? If it's 2 or more away, your controls can still be effective because of the neutrality of the people in between. If it's between you and your immediate customer, I would analyze that with different economics. If I buy service from you and I buy service from somebody else, you can prepend in my direction if you like, but I'm buying the service. I get to choose whether I give the packet to you or to the other guy. Now, that may be a little hard-nosed as an analysis, but from the buyer of bandwidth and the seller of bandwidth, there's one set of rules that apply. Over multiple ASs, another set of rules apply, and then when you go to that more complex diagram and you analyze what happens if you prepend, you can still influence your personal policies of which your links get used by using prepend, even if we're doing what we're doing, by injecting a layer of ASs in between. So with a real diagram, I think we could explain this a bit more, but maybe you see what I'm saying.
Any other answers to the first question? Otherwise, we'll go to Randy. Randy?
I agree with that analysis. I would also add is all you're doing is deciding what the next hop is. The next hop may have a totally different policy and may listen to all those prepends or may not.
Absolutely. And nobody here is making any pretense of end-to-end path control. Right? That's a point I referred to earlier. Is it works now and it's effective because we're only talking about getting these kinds of improvements from controlling one hop, and we all have our marketing claims out there that we've tried not to spend time on here about just how effective it is to change one hop and get these kinds of improvements. So yes, absolutely. We're just changing one hop and then relying on existing policy mechanisms. We're not asking everybody to change how they do their inter-provider relationships.
Woody points out that in a perverse, non-isolated stub transit situation, in fact, the next hop could look at their policy and decide to send it back to you. In other words, when you muck this way with BGP, you can get surprising results.
Very strong agreement on that. I muttered something earlier about the difference between deploying in an enterprise and deploying in an ISP. The looping problems you have to address in an ISP environment are entertaining, and maybe we'll spend a few hours on that next NANOG.
Any other questions from the floor? Well, thank you very much for your kind attention, and thank you very much to the panelists, to Jeremy and Aaron and Robert, Mike and Brandon.